All right, here we have a conical tank with the vertex down that's 10 feet across the top and 12 feet deep. And it says water is flowing into the tank at a rate of 12 cubic feet per minute. Find the rate of change in the depth of water when the water is 8 feet deep. So let's draw a picture of what's going on here. So conical tanks of downwards. Let's see if we can draw this cone. Yeah, it's all right, I guess. So it's a right angle, 10 feet across. So from here to here, one into the other, that's 10. And then 12 feet deep. So from here to the bottom, it's 12. And it says water is flowing into the tank at a rate of 10 cubic feet per minute. So we're told that the change in volume then is 10 feet cubed per minute. So we're given that the change in volume, so dV over dt was 10 feet cubed per minute. So first identify what you're given and can write it in calculus language. And then identify what you want to find in calculus language. We want to find the rate of change. So find the rate of change of the depth of water. The depth of water. So remember, let's just assume that the water. So water is flowing up somewhere in here. So then let's shade that in. The depth of water measured from the bottom upwards, we're going to have that be some height. We're going to have that h represents the length or the height of the depth of water. We want to find the rate of change of the depth of water. We want to find the change in height. So we want to find dh over dt when the water is 8 feet deep. So when h is 8. So that's our goal. Now, now we need to figure out how we can represent this with some equation that we can differentiate. And try to use what you know from geometry and dig deep in your brain and really think. And some of these can be pretty tricky. So let's go working off with this cone. So this cone has a or the cone of the water, the water filled part has how the height of h, and we're also going to give it a radius length from here to here. So halfway, the whole diameter of that portion, we'll just call it r. So that'll be r. Now, we have that the volume of a cone, the volume of a cone is, we should know, the volume of a cone is 1/3 pi r squared times the height. So we have to find some way to differentiate this and get this. I want to find some way to differentiate this and get this from this visual. So, we have variables, volume, radius, and height. We're given dV dt, so that's no problem. R and H is what we got to worry about now. So let's look at a way how we can relate R and H. So I'm going to draw on the side here. We're going to draw the two-dimensional depiction of this cone. So the overall cone, you can think in, if you just cut out, flat, slice, or look at it just in 2D, you make a right triangle here. This right triangle, this length would be half of 10, that would just be 5. The height in this right triangle from here to here would be 12. Now, we can also represent the water level by a smaller right triangle, And since it's within the cone, it's going to be similar to the large rectangle or to the large triangle of the entire cone. So remember, this is the height of the water. Let me shape this in a little bit so you know. This is the height of the water from here to here. And the height is variable, it's changing. So we're going to make that h. And from here to here, that's the length of the radius of this cone, or this portion of the total cone. So we're going to keep that as r. Remember, r, h. And since these are similar triangles, then that means that 5/12 is the same as r over h. Or you can say 12 over 5 is the same as h over r. Either way, we get an equation. So let's go ahead, let's just write something like that. Let's write 12 over 5 equals h over r. And now look, remember, in our equation, we want to find dh dt. So we want to find, it'd be easier if we're going to eliminate the r variables and just have h, because then we don't have to have so much to work with. It'll make it easier for us to differentiate. So let's rewrite this r in terms of h. So we're going to have this multiplied by r, and so that means that 12/5 r equals h. Now, similarly, if we solve this for r, multiplying both sides by 5/12, that means r is going to be 5/12 h. So we have two equations that we can work with, where we have one variable in terms of the other, explicitly in terms of the other. Now, since we want to just have h's in this equation, because we want to find dh dt, we replace r with 5/12 h. So what we get then is that the volume will be 1/3 pi times 5/12 h squared times h. So let's simplify this a little bit. 5 times 5 is 25. So let's put that in front. We have 25. 12 times 12 is 144. Times that 3 there. It should be 432. We'll have over 432. All this multiplied by pi. And h times h is h squared times h will be h cubed. Okay, so now we have an equation for volume simply in terms of h. So now let's differentiate this with respect to time, and then we'll get dh dt, and then we can just plug numbers in and we'll be able to get dh dt for when h is 8. So differentiating this equation for in respect to time, so dv over dt will be equal to 25 over 432 pi. I mean, that's the coefficient. Using the power rule for h cubed, we'll have 3h squared. And remember, h is a function of time, so using the chain rule, this will be times dh over dt. And now we simply just plug in and solve. This is just the algebra part. The calculus part is pretty much done. So we plug 8 in for h, and 10 in for dv over dt, and solve for dh over dt. So then go working this out, we get 10 equals 25, 432. I'm going to put the pi afterwards. So if h is 8, if h is 8, you're going to have 8 squared times 3. So 3 times 64. You're going to have times 192. Parentheses. 192 times pi times dh over dt. And then now, I'm trying to be as precise as possible. We multiply the top by 432 divided by 25 times 192 times 5. So we'll get 10 times 432 over 25 times 192 times 5. That'll be equal to dH dt, dH over dt. And using decimal approximation, that comes out to about 0.28647888976. And dH dt will be approximately 0.28647888976. We're talking about just the change in height, so we're just going to have one-dimensional as our unit, so feet per minute. And there we go.